37 million tons. That is the staggering amount of coffee consumed across the globe every single year. And nearly all of those grounds, that dark, damp, earthy residue left in your filter basket every morning, end up discarded in a landfill. Or perhaps they end up in your kitchen bin, which eventually leads to the exact same destination. You have likely been told at some point that coffee grounds are beneficial for your garden. You might have even tried sprinkling them around your tomato plants or roses, expecting a miraculous transformation, only to find that nothing much happened. Consequently, you gave up. And that is precisely where the story becomes truly interesting, because the individuals who advised you to simply scatter raw grounds on top of your soil were mistaken. The technique that actually works, the one that genuinely revolutionizes the microbial activity within your soil, has been hiding in plain sight. It is a method pieced together from ancient fermentation traditions, mid-century soil science, and a small group of researchers who were willing to view kitchen waste through a different lens. Stay with me, because by the time we are finished here, you will never look at your morning cup of coffee the same way again. Let me explain what is actually occurring in your garden soil right this moment. If you were to scoop out just one single teaspoon of healthy living soil and place it under a microscope, you would discover somewhere between 100 million and 1 billion individual bacteria. You would see fungi threading through the earth like microscopic root systems, protozoa hunting those bacteria, and nematodes grazing on the protozoa. It is an entire predator-prey food web, invisible to the naked eye, operating at a scale so dense and complex that it makes a coral reef appear simple by comparison. That web of life is what truly feeds your plants, not bags of fertilizer or synthetic nutrients. The living community in your soil is responsible for breaking down organic matter, fixing nitrogen from the atmosphere, dissolving locked-up minerals and delivering them directly to your plant roots in forms they can actually absorb. Healthy soil is not merely dirt with chemicals added to it. It is a living ecosystem. Unfortunately, modern gardening, even when well-intentioned, has been slowly suffocating the system. Here is how it happens. Walk into any garden center and observe what they are selling. Bags of sterilized compost, potting mixes designed to drain rapidly and stay clean, and slow-release chemical fertilizers that bypass the soil food web entirely to feed plants directly. On the surface, this sounds efficient. However, what actually occurs is that plants fed with synthetic fertilizers stop sending carbon sugars down into their root zones to feed mycorrhizal fungi because the nutrients are already readily available. There is no need for the plant to pay the fungi for delivery. Over time, the microbial community begins to starve. The soil becomes biologically dead. Now it requires even more fertilizer to compensate because the natural nutrient cycling has completely collapsed. It is a dependency loop, and the companies selling the fertilizer are well aware of it. They may not have designed it this way intentionally, but the economics certainly reward the outcome. And here is the part that makes it personal. You are paying for it. The average home gardener in the United States spends between $200 and $500 every year on soil amendments, fertilizers, and compost. That is an annual expense. Many gardeners report that despite this spending, their yields eventually plateau or decline because the underlying biology of their soil has been compromised. You are essentially renting fertility instead of building it. Meanwhile, every morning you are throwing away something that, if utilized correctly, could begin to reverse that decline for free. This is not some niche permaculture fantasy. I am going to show you the exact mechanism, the science behind it, and the precise method. But first, I want to tell you where this idea actually originated, because the source is not what you would expect. Go back approximately 2,000 years to the highland regions of what is now Ethiopia, where the coffee plant, Coffea arabica, grows wild in the forest understory. The communities living there did not just drink coffee, they composted it. The spent pulp and grounds from their traditional processing methods went directly into midden heaps, essentially communal compost piles maintained alongside their gardens. Soil scientists who have analyzed the earth around ancient Ethiopian agricultural sites in the Harar region have found microbial signatures remarkably similar to what we see in highly productive, biologically active soils today. The connection remained circumstantial for a long time, but it planted a seed, pun fully intended, Fast forward to 1943, a USDA soil researcher named Selman Waksman, who would later win the Nobel Prize in Physiology or Medicine in 1952, was deep in his investigation of actinomycetes. These are a type of bacteria that live at the boundary between soil and decomposing organic matter. Waksman discovered that this group of organisms produces a staggering variety of antibiotics and enzymes that help break down tough organic compounds, including the lignin and cellulose found in plant material. What he noted in his lab notebooks, which was not widely publicized at the time because the agricultural industry had already pivoted towards synthetic inputs, was that certain high-carbon, slightly acidic organic materials created unusually favorable conditions for actinomycete proliferation. Coffee grounds were among the materials he tested. The results were striking enough that they appeared in an internal USDA bulletin in 1947. Then they quietly disappeared from the public conversation for decades. Why did this research disappear? Because the post-war agricultural boom had already committed to the Haber-Bosch nitrogen synthesis pathway. Synthetic fertilizer was cheap, scalable, and politically supported as part of the Green Revolution. Research into biological soil activation simply did not have a commercial sponsor. It did not fit the economic model. And so it accumulated dust in archives while the market moved in a different direction. This is not a conspiracy. It is just how science funding works. Research that serves a product gets funded, while research that replaces a product does not. The knowledge was not suppressed so much as it was simply left on the shelf, underfunded, while the synthetic approach was given billions in development resources. What has changed is that we now possess the tools to examine soil microbiomes in extraordinary detail. DNA sequencing has allowed researchers to characterize exactly who is living in your soil and what they are doing. In the last 15 years, a body of research has emerged, including a notable 2018 study from Oregon State University and complementary work from the Julius Kuhn Institute in Germany, that has begun to rigorously document what coffee ground amendments actually do to soil microbial communities. The results are more nuanced and more powerful than anyone who just puts grounds on their roses has ever imagined. I will get into exactly what those studies found and how to apply it in just a moment. But first, I want to ask you something directly. Have you ever tried using coffee grounds in your garden before? And if you did, what happened? Please drop it in the comments below. I am genuinely curious whether your experience matches what the science says should or should not work. Because as we will see in a minute, the method matters enormously. The same material applied in two different ways can produce completely opposite results. Let us get into the mechanism, and I want you to actually understand this, not just memorize it. I'm going to use an analogy that might seem strange at first, but bear with me. Think of your soil's microbial community as a city, a thriving, complex city. There are neighborhoods, different microhabitats around root zones, in the pore spaces of soil aggregates, and at the surface of decaying organic matter. There are different professions: nitrogen fixers, phosphorus solubilizers, cellulose degraders, predators, and decomposers. There is an economy where carbon is the currency. Organisms that have carbon to spend attract workers. Organisms that run out of carbon get outcompeted and decline. Now, coffee grounds by dry weight are approximately 50% to 58% carbon. That is an exceptionally high carbon load for something you are already producing every single day. But, and here is the first critical thing most people miss, raw, uncomposted coffee grounds release that carbon slowly and unevenly. And they carry compounds that, at high concentrations, can actually be antimicrobial. These include caffeine, chlorogenic acid, and certain phenolic compounds. When you scatter raw grounds directly on your soil surface, you are doing two contradictory things simultaneously. You are offering a carbon feast, but you are also putting up a chemical barrier that many soil organisms cannot tolerate. The result is a patchy, unreliable response. Some organisms thrive while others retreat. The net effect is modest at best and neutral or slightly negative at worst, which is exactly what most gardeners have experienced. The mechanism that actually works involves two phases. Phase 1 is pre-composting, allowing fungal colonization of the grounds before they ever touch your garden soil. Phase 2 is layered integration, incorporating the colonized grounds in a specific way that maximizes their contact with the existing soil food web. Let me walk you through both. When you allow coffee grounds to sit in a moist, aerated environment, even for just 7 to 14 days at room temperature, something remarkable happens. Fungal spores from the environment, particularly species in the genera Marn, Trichoderma, and Penicillium, detect the available carbon and begin colonizing the grounds. You can actually see this happening. First, a white or pale gray mycelium appears, then sometimes blue-green patches if Penicillium takes hold. Most gardeners panic at this point and throw the grounds away, thinking they have gone moldy. That is the opposite of what you should do. That mycelium is predigesting the grounds. It is breaking down the caffeine and chlorogenic acid that inhibit soil bacteria. It is manufacturing enzymes, cellulases, proteases, glucanases that will later accelerate decomposition in your soil. It is essentially doing the hard chemistry so your soil bacteria do not have to. By the time those colonized grounds touch your garden, they are a completely different material. They are a fungal inoculant, a slow-release carbon source, and a biochemical toolkit all in one. Here is the second mechanism, and this one I find genuinely astonishing. Coffee grounds have a carbon-to-nitrogen ratio of approximately 20 to 1. That is a sweet spot. Below 15 to 1, organic materials release nitrogen so fast they can cause a flush of bacterial growth that crashes and burns, leaving your soil temporarily depleted. Above 30 to 1, like wood chips or straw, the nitrogen gets locked up in microbial biomass for months before it becomes plant available. 20 to 1 sits right in the window where microbial communities build steadily and sustainably. They do not spike, they do not crash, they establish. And because coffee grounds also carry small but meaningful amounts of nitrogen at around 2%, as well as phosphorus, potassium, magnesium, and copper, the microbial community feeding on them has access to the full suite of nutrients it needs to actually replicate and grow its population. You are not just giving the city carbon currency, you are also funding the schools, the hospitals, and the infrastructure. Now here is the wait what fact I mentioned I would drop in. Coffee grounds, specifically the silver skin, the thin membrane that clings to the bean and often ends up in the grounds, contain compounds called melanoidins. These are complex brown polymers formed during roasting, the same class of compounds that give coffee its color and much of its flavor. Melanoidins are extraordinarily resistant to rapid microbial degradation. They persist in soil for months to years, and they have a documented capacity to chelate heavy metals. This means they bind to metals like lead, cadmium, and aluminum, and prevent them from being taken up by plants or leaching into waterways. If you live near any kind of industrial site, or if you have inherited land that may have had chemical inputs applied for decades, this is a non-trivial benefit that nobody talks about when they are telling you to put grounds on your roses. There is a third mechanism at play, and it operates at the physical level rather than the chemical one. Coffee grounds, when properly incorporated into soil, improve what soil scientists call aggregate stability. Soil aggregates are the crumbles, those little clods you see when you dig into healthy garden soil. They are created when bacterial biofilms, fungal hyphae, and organic matter bind mineral particles together into stable structures. Those structures create pore spaces. Pore spaces hold air and water. Roots grow through them. And the surfaces of those aggregates are where the most intense microbial activity in your soil happens. It is where the city's commercial districts are. To continue the metaphor, coffee grounds, because of their particle size and their irregular texture, interlock beautifully with both clay particles and sand grains. In clay soils, they act as a wedge, physically spacing the clay platelets apart, reducing compaction and opening drainage channels. In sandy soils, the ground's sponge-like porosity absorbs and holds water in a zone that would otherwise drain past plant roots in minutes. A 2019 study from Wageningen University in the Netherlands found that soil amended with composted coffee grounds showed a 15% improvement in water-holding capacity compared to unamended controls, and a measurable increase in macroaggregate formation within 8 weeks of application. Now, I want to give you the practical blueprint, the exact method that actually harnesses all three of these mechanisms. I have been holding the most important part of this back until now because context matters. Without understanding what you have just learned, this would just be a list of steps. With that understanding, each step will make intuitive sense. You are going to need a few things. First, your coffee grounds. If you do not drink enough coffee yourself, or if you want to scale this up beyond what your household produces, virtually every coffee shop in America, Europe, and Australia will give you their spent grounds for free if you ask. Starbucks famously started their Grounds for Your Garden program. But even independent cafes will fill a 5-gallon bucket for you with a smile because otherwise they are paying to dispose of it. Second, a container with a lid. Third, wood chips or dried leaves. Fourth, water. That is the complete materials list. Here is the process. Start by combining your coffee grounds with roughly an equal volume of shredded dry leaves or small wood chips. This is not optional. The grounds alone, piled more than 2 inches deep, will compact into an anaerobic, waterlogged mass that encourages the wrong kinds of fungi, the pathogenic ones. The carbon-heavy bulking material keeps the pile aerated, maintains pore space, and adjusts the overall carbon-to-nitrogen ratio to something closer to 30-1, which creates a slightly slower, more stable decomposition environment. Mix them thoroughly, then lightly moisten the blend. You want it to feel like a wrung-out sponge. Not soaking wet, not bone dry. Put the lid on the container, leaving a small gap for airflow, and wait. 7 to 10 days at room temperature, or 2 to 3 weeks if your nights are cold, is all it takes for visible fungal colonization to establish. You will see the white mycelium threading through the mixture. The smell will shift from coffee to something more earthy, almost sweet, like a forest floor after rain. That smell is actually a compound called geosmin produced by Actinomycetes, the exact microorganisms Waxman was studying back in 1943. It is not a bad smell. It is one of the best smells in biology. It means the process is working. Once you see that mycelium and catch that earthy scent, your pre-composted grounds are ready. Now, most people get this part wrong. They apply it as a mulch, piling it on top of the soil surface. That does some good. It will break down eventually and the organisms will migrate downward. But you lose 60% to 70% of the benefit. The correct application is shallow incorporation. Use a hand fork or a trowel to work the material into the top 4 to 6 inches of soil around your plants. Do not go deeper. The aerobic organisms you have cultivated need oxygen, which in most garden soils exists primarily in that upper zone. Bury them deeper and you are placing them in a low oxygen environment where many of them will go dormant or die. The rate of application is approximately 1 cup of pre-composted material per square foot of garden bed, worked into those 4 to 6 inches of depth. Apply once at the beginning of spring and again at the start of autumn. 2 applications per year is sufficient. More is not better. Overdoing it, even with this pre-composted version, can tip the pH too far acidic in some soils and suppress the very biology you are trying to cultivate. The second mistake most people make is related to pH, and it is based on a myth that has taken on a life of its own. You will hear everywhere that coffee grounds are acidic and therefore great for acid-loving plants like blueberries and azaleas. Here is what is actually true. Fresh unbrewed coffee grounds are mildly acidic with a pH around 6.0 to 6.5, but spent grounds, the ones left after brewing, have had much of their acidic compounds extracted into your cup. Their pH is typically between 6.5 and 6.8, essentially neutral. And after 7 to 14 days of fungal pre-composting, the pH stabilizes even further toward neutral, often landing between 6.7 and 7.0, which is incidentally exactly the range in which the widest variety of soil microbes thrive. So you can stop worrying about whether coffee grounds will acidify your blueberries. They probably won't. And you can start using them on vegetables, fruits, herbs, and ornamentals equally. The acid-loving plant claim is one of those garden myths that gets repeated so often it starts to feel like fact. Now you know better. For gardeners who want to take this to an advanced level, there is a variation that amplifies the results significantly. After your initial 7 to 10-day colonization period, add a small amount of finished vermicompost or worm castings to your coffee ground mixture. roughly 10% to 15% by volume. Worm castings are extraordinarily rich in microbial diversity. The species count in quality worm castings can exceed 10,000 distinct bacterial species per gram. When you blend that diversity into your coffee ground fungal colony, you create what is sometimes called a polyculture inoculant, a material that simultaneously delivers fungal biomass, bacterial diversity, and pre-digested carbon all in one application. Researchers at the University of California, Davis, working on urban soil remediation projects, have documented that polyculture inoculants, even homemade versions, can establish measurable microbial biomass increases in degraded urban soils within as little as 3 weeks of application. One more climate note. If you are in a hot, arid climate, your pre-composting period will be shorter, but you will need to monitor moisture more carefully. In those climates, the grounds can dry out before fungal colonization fully establishes. Miss the container lightly every 2 to 3 days if you live somewhere consistently above 30 Tsunamegisu. In very cold climates, you may want to pre-compost indoors where temperatures are more stable. Then store the finished material in a sealed container in a cool, dark place until the soil thaws in spring. The fungal community will go semi-dormant at low temperatures, which is fine. They will reactivate when soil temperatures warm. Now let us talk about what you are going to see after you apply this. Week 1. Honestly, nothing dramatic. And this is the moment where impatience becomes the enemy of success. The microbial community you have introduced is establishing itself, learning the new terrain, and negotiating territories with native soil organisms. You might see some surface whiteness near the application zone if conditions are moist. Do not panic. That is just the fungal hyphae doing exactly what they are supposed to. Week 2 to week 4. This is when the transformation becomes visible through indirect signs. Your soil surface will change texture. It will feel softer under your fingers. When you press a handful together and release, it will hold its shape slightly, a sign of improved aggregation. Earthworms will begin to concentrate near the application zones. Earthworms are not just the result of healthy soil, they are also accelerators of it. Their castings are 14 times richer in available nutrients than the surrounding soil. When earthworms move toward your amended zones, that is one of the most reliable indicators that your soil food web is awakening. By month 2, if you applied in spring, you will likely notice a visible difference in plant performance. Not just growth, but a kind of resilience. Plants grown in biologically active soil are sturdier. Their cell walls are thicker because they have had access to the full spectrum of micronutrients that the microbial community unlocks. They are more resistant to fungal pathogens, partly because the beneficial fungi you have introduced compete directly with pathogenic species for space and resources. One of the most consistently reported observations from gardeners who switch to biological soil management is that their plants handle drought and heat stress noticeably better than before. This is not a coincidence. Plants in biologically active soil develop deeper, more branching root systems because the mycorrhizal fungi they partner with are actively exploring the soil for water and mineral deposits in exchange for carbon sugars. It is a trade deal, and when that deal is functioning, plants have a support network that no bottle of fertilizer can replicate. Something that might look like failure. Around weeks 2 through 4, you might notice some yellowing of lower leaves on certain plants. This is real. What is happening is that the shift in soil biology can temporarily alter nutrient availability as the microbial community reorganizes itself. Nitrogen that was being delivered by one pathway may be temporarily rerouted as populations of organisms shift. This is called the transition effect. It is documented and temporary. Within 4 to 6 weeks, the new equilibrium establishes and nutrient delivery typically exceeds what it was before. Knowing this in advance keeps you from adding synthetic fertilizer at exactly the wrong moment, which would disrupt the biological transition you are trying to establish. Here is what I find most striking about all of this. That coffee sitting in your filter basket right now traveled probably from Ethiopia, Colombia, Vietnam, or Guatemala. It was grown in soil. It absorbed water and minerals through root networks fed by microbial communities. It was roasted, ground, and brewed. And what is left, the grounds, still carries within it a biological potential, a carbon library, and a set of chemical compounds that soil organisms recognize and respond to. The relationship between decomposing organic matter and soil biology is ancient, older than agriculture, older than humanity. The organisms in your soil have been breaking down plant material for hundreds of millions of years. When you give them something they recognize, something rich and alive and complex, they wake up. The industry gave you a bottle of liquid to pour, simple, scalable, and profitable. And it works for a while, but it does not build anything. It rents fertility, one application at a time. What you are choosing when you do this instead is to invest, to build a biological asset in your soil that compounds over time. Every year you do this, your soil gets better. The microbial community grows more complex, more resilient, and more capable. Plants perform better with less intervention, water bills drop, fertilizer bills drop, and pest pressure drops because plants in biologically active soil produce their own defense compounds more effectively. The economics flip completely within 2 to 3 growing seasons. Share this with someone who has told you coffee grounds just do not make a difference in the garden, because they are right. The way most people use them. The method matters, the science is there, and now so is the knowledge. Next week, we are going to go somewhere that will challenge everything you think you know about watering. There is a technique being used by subsistence farmers in northern India and parts of the Sahel region that reduces water use by over 60% while actually improving yields. It has been documented and replicated, yet almost no one in the Western gardening world knows it exists. You do not want to miss that one. If this story changed how you view the waste in your kitchen, please subscribe and like the video. We are uncovering the agricultural history and science that has been overlooked for too long. Let's cultivate a better future together. The next treasure of knowledge will be revealed very soon.